Right now, somewhere in southern China, a factory the size of 200 football fields is spitting out one finished battery cell every single second. Not every minute, every single second. And if you think that sounds insane, wait until you hear what it takes to make just one of those cells, because the process is so extreme, even your breath could destroy an entire batch. This is the story of how the world's most powerful battery factory turns raw powder into the beating heart of every electric vehicle on the road. And why a single mistake, thinner than a human hair, could cause a catastrophic explosion. Let's get into it. This one's a deep dive. The factory we're talking about belongs to CATL, Contemporary Amperex Technology, the largest battery manufacturer on the planet. They control nearly 40% of the global EV battery market. Ford uses their cells. Tesla uses their cells. BMW, Volkswagen, Mercedes, they all depend on CATL. And CATL has poured billions of dollars into a sprawling network of gigafactories across China and beyond. Their Hungarian facility alone carries an investment tag of over $8 billion. Their newest plant in China's Guizhou province required nearly $1 billion investment just for Phase 1, and it cranks out 30 gigawatt-hours of batteries per year. Add up all their production bases, from Ningde to Guizhou to Shandong to Germany, and you're looking at a combined investment well north of $10 billion. But here's what blows my mind. A single production line inside one of these factories stretches 1,500 meters long. That's almost a full mile of machines, robotic arms, and conveyor systems, all working in perfect sync with a 95% automation rate, monitored by over 7,000 quality control checkpoints in real time. The World Economic Forum recognized CATL's Z factory in Ningde as the first ever lighthouse factory in the entire lithium-ion battery industry, their term for the most advanced, most digitized manufacturing operations on the planet. And the defect rate? 1 in a billion. Let that sink in. Out of every billion cells CATL produces, statistically only one might have an issue. That means fewer than 1 in every 10 million electric vehicles using their batteries could ever have a cell-level defect. That's not just good, that's nearly perfect. So how do they actually do it? Let's walk through the 10 steps it takes to build a single EV battery cell, from raw powder to road-ready power. Step 1. Mixing. Everything starts with a recipe. And just like baking, if you mess up the ingredients, the whole thing falls apart. Machines measure out active materials like lithium, nickel, manganese, and cobalt. These get combined with binding agents, conductive additives, and a solvent to create what's called a slurry, a thick, dark paste. A planetary ball mill, and kind of like an industrial flour kneader on steroids, mixes everything together until the consistency is absolutely uniform. The cathode gets its own slurry, the anode gets a separate one. And the precision here is critical because the viscosity and density of this slurry will directly impact how the final battery performs. Too thick, too thin, wrong ratio, and you've got a cell that won't hold a charge, or worse, one that could fail catastrophically. To put the raw materials into perspective, a single average EV battery with a 60 kilowatt-hour capacity contains roughly 115 pounds of graphite, 77 pounds of aluminum, 64 pounds of nickel, 44 pounds each of copper and steel, 22 pounds of manganese, 18 pounds of cobalt, and 13 pounds of lithium. That's over 400 pounds of refined minerals mined, processed, and purified, packed into every single battery. And every ounce of it starts right here in the mixing room. Now here's where it gets wild. Step 2. Coating. That slurry now has to be painted onto ultra-thin metal foils. The cathode slurry goes onto aluminum foil. The anode slurry goes onto copper foil. And we're not talking about regular kitchen foil here. CATL uses copper foil that's just 4.5 microns thick. To put that in perspective, the average human hair is about 70 microns. This foil is 15 times thinner than a strand of your hair. The coating machines apply the slurry at speeds of over 260 feet per minute onto rolls of foil that stretch over 2.5 miles long. Both sides of the foil get coated with microscopic precision, and any unevenness, even a fraction of a micron, could ruin the cell's performance down the line. This single step determines how evenly your battery charges, how long it lasts, and whether it performs consistently over thousands of cycles. But the next part, this is where the factory basically slows to a crawl. Step 3. Drying. Here's a fact that surprised me. Drying accounts for 48% of the entire battery manufacturing process. Nearly half. After coating, those wet electrode sheets need to be dried thoroughly using massive heated ovens and vacuum systems. The foils pass through multiple different temperature zones, each carefully calibrated to remove moisture and solvents without warping the material. If any moisture remains trapped in those layers, it will react with the lithium later in the process and destroy the cell from the inside out. Some drying stages can take anywhere from 12 to 30 hours per batch. This is the slowest and most energy-intensive part of the whole operation. And it's exactly why building batteries at scale requires such enormous factories and such enormous investment. And speaking of things that can ruin a battery, let's talk about the air itself. The rooms where these batteries are assembled are called dry rooms, and they might be the most extreme manufacturing environments on Earth. The humidity inside is kept below 1%. The dew point sits between -40 and -76 degrees Fahrenheit. To give you a comparison, the cleanliness standard inside these rooms is equivalent to a cardiac surgery operating room, except the dry room is 1,000 times larger. The air gets filtered 25 times every single hour. In any given space the size of your fingertip, there are fewer than 10 dust particles. And here's the part that sounds made up but is absolutely real. If a worker were to simply breathe without proper protective equipment, the moisture from their breath could contaminate an entire production run. That's how sensitive lithium is to water. Even a trace amount of moisture triggers chemical reactions that degrade the electrodes, short-circuit the cell, or in the worst case, cause thermal runaway, which is a fancy way of saying the battery violently catches fire. This is precision engineering on a level most people never think about. All right, back to the steps. Step 4. Pressing. The dried electrode sheets now go through a roller press, two massive steel cylinders that compress the material to increase its energy density. This process is called calendaring. Proper compaction reduces internal resistance, minimizes polarization losses, and extends the battery's total cycle life. If the sheet isn't perfectly flat after pressing, everything downstream falls apart, so every single millimeter counts. Step 5. Slitting. Those electrode sheets are still hundreds of feet long at this point. In the slitting phase, precision blades cut the electrodes down to the exact dimensions needed for the final cell. First, vertical cuts divide the sheet into strips. Then, a notching process cuts V-shaped tabs into the uncoated edges. These tiny tabs will become the positive and negative terminals that connect the cell to the outside world. To your car, your motor, your wheels. Step 6. Stacking. Now comes assembly. For prismatic and pouch cells, the types CATL specializes in, the cathode sheet, the anode sheet, and a thin separator membrane are stacked on top of each other in precise alternating layers, like a microscopic lasagna. The stacking method requires incredibly high technology and precision, but produces cells with better energy density because there's virtually no wasted space inside the casing. Some manufacturers use a winding technique instead, like rolling up a sleeping bag, which is faster but less space efficient. CATL's stacking approach is slower, but produces a demonstrably superior product. And now we reach a step so delicate it has to happen in a vacuum. Step 7. Electrolyte filling. The stacked cell assembly is placed into its casing, and then the air is completely evacuated to create a vacuum. Under that vacuum, a precise amount of liquid electrolyte is injected through a nozzle. The electrolyte is the lifeblood of the battery. It's the substance that allows lithium ions to travel back and forth between the cathode and anode during charging and discharging. The vacuum ensures the electrolyte penetrates every single pore in the electrode material. If even one tiny pocket is left dry, that part of the cell won't function, reducing capacity and creating a potential weak point that could cause failure down the road. After filling, the cell is carefully sealed. But here's the thing, the battery still isn't alive yet. Step 8. Formation. This is where the real magic happens, and it takes forever. Formation is the process of charging and discharging the battery for the very first time. It's done at an agonizingly slow rate, typically at a 0.1 C rate, meaning it takes around 20 hours just for a single charge and discharge cycle. During this initial charge, a critical protective layer called the Solid Electrolyte Interface, or SEI, forms on the surface of the anode. This ultra-thin layer is what protects the battery for its entire operational lifespan. It allows lithium ions to pass through while blocking electrons, preventing the electrolyte from decomposing further. If the SEI layer doesn't form properly, the battery will degrade rapidly, lose capacity within months, and could even become a safety hazard. Formation is the single biggest bottleneck in all of battery manufacturing, and it's the step that separates a mediocre battery from a world-class one. Step 9. Aging. After formation, the cells are stored at carefully controlled temperatures and humidity levels for extended periods, sometimes lasting days. This aging process allows the electrolyte to fully permeate and distribute evenly throughout every layer of the cell. The batteries are continuously charged and discharged during this window, and any gas that builds up inside the cell is removed through a degassing process. This cycle of aging, charging, and degassing is repeated multiple times to make sure the cell's internal chemistry has completely stabilized before it moves on. Step 10. Testing. Every single cell goes through over 100 different quality tests before it ever leaves the factory floor. Smash that like button, share it with someone who drives electric or is thinking about making the switch, and if you're not subscribed yet, what are you waiting for? We break down the most fascinating manufacturing stories on the planet right here on this channel. Hit subscribe, turn on that notification bell so you never miss a drop, and I'll see you in the next one.